Good morning, everyone. Now we are on the second day of TUAC. Today we have also a distinguished speaker, Professor İlker Birbil, and Professor Ulus is going to moderate this session. Now, I want to keep it short and give the word to Professor Ulus.
Thank you. So today we have a talk from Professor Birbil from University of Amsterdam, and let me introduce the Professor Birbil first before starting his talk. So Professor Birbil is a professor in AI and optimization techniques for business and society at University of Amsterdam, where he is currently the head of business analytics section. He received his PhD in 2002 from North Carolina State University with a major in industrial engineering and minors in operational research and mathematics. Most of us know him from Sabancı University, where he was a faculty member at there in Istanbul from 2004 to 2018. Then he had the chair in data science and optimization at Erasmus University Rotterdam for 3 years. Now he is at University of Amsterdam. His research interests center around optimization methods in data science and decision making. Lately, he is interested in interpretable machine learning and data privacy in operational research. Today, he will give a lecture on exciting world of interpretable machine learning. I think this will be a super exciting talk. And Professor Birbil, it is a great pleasure to have you here, and the stage is yours. You can share your screen.
All right, thank you very much. It was just, you put a lot of pressure on me, Doğan, and I'll try my best.
I'm sure.
All right. Thanks again, and the IEEE Turkish section for inviting me over. That's really an honor to be here. And it's always nice to talk to the younger people and then get their feedback. So I hope this will be something that I'm talking about my own research, but not only that, we'll have some chance to really discuss what can be done in this field. And I wanted to call it this exciting work because this is really a developing field. I'm learning myself as well. And I'll just try to briefly introduce what's going on and what I am trying to do with my team in University of Amsterdam. So that will just sum up everything. And maybe in the very last part, I'll just try to give you a few slides where I'll try to be more critical so that hopefully it will open some discussion for us. All right, let's give it a try. All right. I think everybody now more or less knows what a machine learning algorithm does. Of course, it's a supervised machine learning algorithm, but the core idea is that there will be a vector of features, and these vector of features are really mapped to a label. And the question about machine learning is really what kind of a thing that we can really fit in here. So this could be, for instance, a decision tree, as you see here. This could be a complicated neural network, some sort of regression, and it can be also an ensemble method. But the thing is, this fitting, we don't really know most of the time. If we knew what that fitting was, we wouldn't have needed any one of these algorithms. But then some of these algorithms, they're really performing very well. We are obtaining really good results, but we cannot really explain them. I mean, if you really look at linear regression, for instance, that you can probably remember from your elementary statistics courses, that's a very nice, very beautiful method. We can talk about it for days. There are books written on it, and it's really very well examined. But we also know that some of these algorithms are not really performing that well in terms of, for instance, accuracy, or if you will, prediction. So people now talk about having more sophisticated methods to come up with a mapping that will really properly tell us the relationship between X and Y. Now, why is it really important? Now, if there is this algorithm that you're using and you're using it for decision making, then you should be able to explain it. So this is just bare human rights, if you ask me. So for instance, there had been some cases in the past, and there was this algorithm used to hire or fire teachers, high school teachers in the US. And it turned out that this algorithm was really doing something crazy. It was just even firing some teachers, which are by their students known to be really good teachers. So this really raised a lot of anger, and then people started talking about it, and there was these courts and so on. So the problem with that was this algorithm that they used was a black box algorithm. people couldn't really explain why it was really deciding upon that firing or hiring decision. So in the recent years, like more recent work, and Cynthia Rudin is one of the important scientists in this area, people started to look into these black box models, the models that we cannot really explain. Maybe we are really overshooting. We don't need an algorithm that's a black box for these simpler cases. So maybe there is an algorithm which is itself explainable. And of course, this really goes on in many different fields. For instance, this is an example from, let's say, the finance industry. And over there, this is also a regulated area. So think about the case. You go to the bank and the bank doesn't give you a loan. And you're asking for this loan and they're rejecting you. You have the right to go back and ask them why you're rejected. So which means that if they're using a sophisticated algorithm which they cannot explain, this is not acceptable. Regulated meaning that is by law, they have to give you a proper explanation. And this proper explanation is important because then maybe you can improve it, whatever it is that you need to do to maybe able to get this loan. So explanations are very important. We cannot just blindfoldedly use the algorithms in every area. There are some areas, for instance, let's say we are trying to really find the pictures of our aunt in our phone. So this is a prediction problem, and that prediction problem maybe does not require explanation. But when people are involved and when there's a decision making, interpretations are extremely important. So what goes on? Why don't we really use these simpler algorithms? Now there is this trade-off. This is the accuracy part and this is the interpretability part. So what happens is there's all these black box models, like these deep learning, support vector machines, whatnot, and they're very, very powerful algorithms. So they're very accurate. On the other hand, we have linear regression, decision tree. These are not as accurate as these sophisticated methods, but they're white box, or sometimes they're called glass box, meaning that they're really easy to explain. Okay, so the core, one of the core research areas is, can we really just maybe push this down? Okay, meaning that it will become interpretable. Okay, and the accuracy may also stay here. So the thing is, can we really come up accurate and interpretable models? Now, of course, many people are working on this, and I did some sort of a taxonomy, and especially the ones that I am kind of interested in. And these are basically giving some examples. And as I said, since it's a very, very hot topic, many researchers are already producing many new algorithms. So I'm not going to claim that this is up to date, but I think the taxonomy itself is just fine. So what kind of approaches we are talking about? So if I really look at these approaches, there is this two groups, one of them called local and global. And here is a core idea between the distinction between local and global is, when it's local, you're going to give an explanation for just one sample. Remember the example that I gave you about this getting a loan. You're rejected and you want an explanation for yourself. You don't need to really understand the entire algorithm, what it does to every sample, but you're just interested in one sample, which is in this case, yourself. Global, as the name implies, this time you're going to just try to give an explanation to the entire model, entire machine learning model, what it does. That's a global explanation. There are also some approaches which are customized and some are agnostic. And customized meaning that, for instance, you have an explanation method, and this explanation method only works with, let's say, support vector machines. So it's a really customized interpretation approach. Agnostic meaning that they don't really care what kind of a model you give. Support vector machines, deep learning, random forest, it doesn't really matter. Whatever you give to them, they will give you an explanation. So that is called model agnostic. And the last branch is about inherent and acquired. Inherent meaning that the algorithm, like linear regression, itself is interpretable. So the algorithm or the decision tree is basically, when you really run it and when you look at what it does, it's really clearly explainable. And acquired meaning that there is an algorithm, and this algorithm, which is maybe a black box algorithm, and you are just going to use some other interpretable algorithms to explain them. So they are really acquiring the knowledge from the already trained black box algorithm. And then I put this color coding, and these are a couple of examples. Some of them are very famous, like Lyman Shep. And due to my background, I am more interested in optimization. I also try to put the ones about optimization here mainly. And the last set of algorithms are the ones that we are trying to develop in University of Amsterdam. I'll be talking about those. And as I said, there are many more algorithms, but I would guess most of these algorithms that are currently being developed, they can be also put into this taxonomy. So what do they do? What do we mean by that? They just generate some plots, for instance. This is an example of Lime. They're just trying to give you a local explanation. Lime, as you can see, it's just using this local. So Lime gives you local explanations. Same as SHAP. SHAP also gives some local explanations. They produce these plots, a feature versus a score, or sometimes they produce this type of weighted plots. So these are different weights of the rules. And these rule business is also very interesting because people find it very easy to understand, meaning that if you really look at a rule is just something we also use in our daily lives. Right? It's a decision. So if this is your salary is less than 35,000 and your age is more than 25, then you can get the loan. That type of explanations are usually quite liked. And the ones that I have really put in here, these are all optimization based. So I'll be talking about them a little bit. And on top of this today, I will also mention counterfactual explanations. And counterfactual explanations basically say that there is this sample for a trained model, suppose that is a support vector machine. And the support vector machine really rejects this, labels it as reject, like the loan example that we were talking about. Then basically the counterfactual explanation is that for this particular example, which is rejected, can we really find it close enough, meaning that quite similar another sample, which would have been accepted. And apparently this is a nice explanation and it's a local explanation. And I'll be talking about those as well. Now, are there any tools for those among us who are really keen on coding and trying things out? Yes, there are. There is this InterpretML tool by Microsoft people. And as you can see, it's also really developing. And I have already mentioned a couple of these. For instance, we talked about SHAP, and as you can see, SHAP, for instance, is now customized or for these kernels. And for instance, this is trees. And there is this Lime, I mentioned that, and of course, decision tree itself is a glass box model. So these are all available through this Python package. Now, what do we do in UvA? UvA is University of Amsterdam, sorry. So first one that I want to talk about uses this linear regression or the linear models. And this is a very, again, interesting line of research, not only for us, but the linear models are usually accepted to be quite interpretable. And people are trying to do many things, not just us, but people are also trying other algorithms where the linearity comes into picture. And I'll tell more about that. And this is a joint work with my university, University of Amsterdam, Erasmus University of Rotterdam, and Sabancı University. And this is sort of my history, basically. I worked in these three universities. I will also talk about trees and rules. These are also, as I mentioned a couple of minutes ago, these are also considered to be interpretable. And I'll be talking about trees and rules. So this is a tree, and this is just a rule. And the relationship is very clear. The red nodes that you see here, these are all rules. So this is a rule, this is a rule, and so on. Again, with Erasmus University. And the last one is about the counterfactuals. And there we work with MIT, my team and our team and MIT team, we work together on another package. And I will use it to explain these counterfactual work. Okay, let's get started. Now, what's really nice about linear regression? We really like to come up with a model. As you can see, these are the features, x1 to xp, and they are all associated with weights. And there is this, of course, the average weight, if you will. Okay, we are basically trying to come up, these are the data points. We are really trying to come up with a linear fit. Now, why do people like it? Because as you can see, for each feature, you are going to get a weight. And that weight can be positive or negative. So they're basically saying that the output will change linearly with respect to this weight in a positive way or in a negative way. So people find this very interpretable. And on top of that, due to this linear structure, there is a tremendous well-developed statistical literature and statistical research, where you can also talk about the confidence intervals. You can talk about many things when it comes to linear regression. People do like linear regression. And what happens here is that they are not that accurate, and they're considered to be interpretable. So if you have a linear model, you're really working with the interpretability side. And then if you really push this in, we may lose accuracy. And our idea was, can we really do something about that? So this is what we proposed. In fact, we proposed this as a meta-learning algorithm, which can really work with any machine learning method. The core idea is, and I'll keep this brief, this is the data set. So suppose that this is an X, which is a matrix, and this matrix is just, each row is a sample, and it's a large matrix. We split this matrix into subsets, as you see, X1 to Xm, and for each subset, we fit a model. And this model can be any machine learning model. Then we combine them and do a global fit. So as I said, I'm not going to go into the details that much, but the core idea is, so there are these regions, which are basically these subsets. If we really can select them in a clever manner, we can have a better fit for those local subsets. A good example is this one. As you can see, this basically these blue dots are the training data set, and the orange dots are the test set. And the actual function, as you can see, it's a sinus function. What's happening here is that if you try a linear regression will perform very bad because this is a highly nonlinear function. So what we are saying that we will just take the subsets, this subset, another subset here, and for those small, let's say, line segments, we are going to have these linear fits. That's why you see many linear fits. And if we can really combine them in a smart manner, maybe we can approximate this actual nonlinear function. Now, does it work well? It does work quite well, but this is, of course, for general functions. I'm not going to talk too much. And we have really compared it with many powerful methods, including gradient boosting, random forest, support vector regression, and vanilla neural networks. So it does perform well. But as I said before, I'm not going to spend too much time on its performance, because these things, as you can see, they all perform quite well. So all I want to say is that less is a competitive method. Now, can you use it? We have a package, and you can find it on this website, and we give some different results and how fast it can really perform in time. This is a logarithmic scale. We are pretty good. I mean, compared to other ensemble methods, we are doing a good job in terms of speed. And you can also parallelize it, which is not super exciting because we have these subsets. These subsets can be trained in parallel. And you can have the code and try it out immediately. LessLearn also involves classification. This LessLearn MPI, which is the parallelized version, that only includes regression. But LessLearn, if you want to play around, it has both classification and regression. Now, having said this, how does it play a role in interpretability? Now, that was a discussion about this. Here is, I like this slide a lot because that also tells you what we mean by a local explanation. Here we go. So suppose that I'm going to use one of these linear models, linear regression, lasso, elastic net, and I'll use it everywhere for local fits, like in the picture before this nonlinear function that we have seen, and also in the far end, which means that whatever we are predicting is a combination of linear functions, right? Because there's this function, another function, and so on. They're combined together and obtain another linear function. And if you work out the simple algebra, this is what comes out of it. So y0 hat is your prediction. This is what you want to predict when somebody gives you an x0. And what happens, remember, in linear regression, we had only this beta vector, beta 1, beta 2, up to beta p. Instead of that, we have these betas dependent on x0. This is a very nice local explanation, because in linear regression, you will have just one beta, which is a global explanation. Now, per x0, that's the sample set, you give different betas. So that's a very nice local explanation. Now, these results unfortunately changed a little bit, but I'll still keep it in here. Some of my friends in Turkey, they tried this algorithm on demand forecasting, and there are 400,000 samples and this many features. They tried Lasso. Lasso basically gives you just one beta. It's a globally interpretable model. And apparently the company was already using LightGBM, so they also tried LightGBM, which is a very powerful method, by the way, but it's black box, so they have to use SHAP to explain it. Remember, if it's a black box model, to interpret it, we need an additional model, and SHAP also gives local explanations. This is the mean square error of Lasso, and this is mean square error of LightGBM. And this is with, again, less, but everywhere we are going to use linear models, and the linear models are themselves Lasso. And this is, remember, just a local explanation. And it turns out that we are performing quite well. Now, later on, I have to really warn you about this. We realized, they realized that they were using, they were scaling the data for these two, which makes sense, but they didn't need to scale it here. When they didn't scale, they improved this mean square error. But what is the advantage? The advantage is basically, this is the model that you're fitting. And then after fitting this model, you have to explain it. And SHAP is just an approximate explanation. But if you use less, you're going to get an exact explanation per sample. It's not as good as a global explanation, but since this is a local explanation and this is a local explanation, this gives you exact local explanation. Okay, that's one example. And then it returns only this many features. You can also come up with this global feature importances and so on. People do like it and find this also interpretable. So apparently for this problem, to obtain these results, this is like the 12th feature is the most important one, and feature 64 is the second important one, and so on. Now, one thing we did so far is about the linear regression, how good it is and how it will be helping us. Now I'm going to move to rule discovery. Now, random forest or boosting methods, they're both on the screen, and they produce all this ensemble of trees. In boosting, if you use the default classifier, that gives you these basically the trees. Now, what happens is they have many rules. If you think about all these trees, let's say 100 trees, you will have thousands of these rules. One idea that we have is if somebody trains this model, random forest or gradient boosting, can we just do some sort of cherry picking, right? It's like picking apples. Can we just pick some of these rules, but not too many of them, and give an explanation to the trained model? That's we call rule extraction. And the next step, which is natural, maybe we don't need these trained models. Can we generate our own rules in tandem? So we generate one rule, we generate another rule, and so on. That we will call rule generation. And the core idea is if we have fewer rules, then maybe that fewer rules could be interpretable. We can explain what's going on with them. And hopefully they will be also accurate. So the overall, I'm not going to spend again not too much time on this, but the nice thing that I want to draw your attention, this is an optimization problem with constraints, and constraints will play a role very soon. And the idea is here, I'm going to really have these many rules. As you can see, these are the WJs that we are trying to optimize. And we have many rules, and these rules can come from, in the case of rule extraction, from the trained model, trained ensemble, or we can generate these rules step by step. So that is the J that you see here. The first part is cost of using rules. And for each rule, there will be a corresponding cost and weight. What could be a cost? If a rule is very long, then we are going to give the rule length as a cost. And why we want to minimize it? Because the shorter the length of the rule, the easier to understand for the decision maker. And the second part is about the misclassification. So, or the total loss from misprediction. Basically, by using these rules, you are going to make a prediction. And if that prediction is incorrect, it will be penalized. So this also naturally shows in the objective function that we are trying to minimize the number of rules or sort of weighted rules. And we also want to keep it accurate. Now, how does it perform? A couple of examples. These are the accuracies. Random forest and AdaBoost are trained. And these are the accuracies of those two models. And remember, rule extraction requires a trained model, and the same random forest is put into rule extraction and AWS here. And this is the rule generation. As you can see, AWS performs the best, but these are also quite close. But the important part is the number of rules. Random forest uses this many rules, and we obtain, for instance, with RAG, this accuracy by using only 24 rules, or sometimes 20 or 19 rules. So which means that we are getting close in accuracy, sometimes even doing better at, because it's 84 and this is 90%, and giving some sort of less number of rules to explain. And not only that, you can also talk about the weights of the rules, because remember, in the objective function, we have weights for each rules. We can also say that these are not just any rules, but we can also sort them out and saying that this is the most important rule, like a feature. This time we are going to give rule importances in a way. Okay, if you want to really know more about this, there's a YouTube video, and this is not really up to date, unfortunately. We are working on it, the code and the paper. Hopefully, within a month or so, the paper will be updated, excuse me, and also the code. Now, one important thing, remember, I said that I'm very keen on using constraints, okay? And another important thing in interpretability is fairness. So this is a very old example, and this is taken from Hu et al. And Rudin is one of the authors. So the data set is famous, the COMPASS data set, and let me try to tell you what it is. They're trying to understand whether a person will be committing crime again, okay? Or what is the likelihood of a person to commit a crime, okay? They were using this algorithm. That's the algorithm was called COMPASS, and that's why they called COMPASS data set. It turns out that, and this is what they did in their paper with this optimal sparse decision trees, they came up with this accuracy, 66.9. That is the accuracy that they obtained. And it is just a simple decision tree. It's very nice because it shows many problems. Apparently, if you just look at whether a person had committed crime in the past, and if their age is, let's say, young, and so on, or they really committed some crimes when they're really young. So this thing basically shows that either there is something wrong with the data set, or the decisions that are being taken are quite biased. So it's not fair to certain individuals. So people are very much interested, and you can imagine that in real life, this is also a very critical issue. Like, are we going to really give less loans to people with different ethnical backgrounds? Of course, if you start using all these black box algorithms may be using this information, if that information is in the somehow creeped into the data set, it's maybe using that data set to make these decisions. In terms of accuracy, it may be really accurate, but the thing is, it's not fair at all. Now, this is 66.9. What we did, and random forest and AWS, you might also ask, as you can see, it's slightly above. It's a very, very nice, clear explanation with a slightly worse accuracy. I think this is very acceptable compared to 68%. Now, remember, this was our original model that we used for RAG and RAGs. And we decided to add fairness constraints. Now, that's the good thing about using optimization, especially constraint optimization, because we can easily add these constraints. For general decision trees, random forest, this is not possible to add these constraints. So we are adding these constraints, and I'm not going to tell you that much, but the core idea is inaccuracies that you're committing in two different groups, okay, they should be close to each other. So meaning that if you're going to reject, let's say 5% of females, you should also really reject 5% of males. Okay, so you want to have these two groups to be balanced. Now, if you have these fairness constraints, the new algorithms become fair RAGs and fair RAG. And I'll show you a couple of results whether it works. Remember, these were the accuracy scores of random forest and ADA. We are getting extremely close. And we are also obtaining these results only very few rules. Look, if you look at random forest and ADA, they are generating this many rules, and we are generating only these rules. And this was the accuracy obtained by Rudin et al. So we are almost the same, slightly above. And when it comes to the unfairness score, there is a metric to measure the unfairness, especially our fair rocks with the random forest is quite fair. The lower the better, by the way. So, and the last part, in the remaining 12 minutes or so, I'm going to talk about counterfactual explanations. But to be able to talk about the counterfactuals, this is the third work that I promised, I need to really introduce you what optical does. Now, we call this constraint learning, and the idea is extremely simple. So here is an optimization problem. Please don't get into the details. They are not really important. There are a bunch of decision variables, some additional variables, and some predicted outcomes. Those are, I think, clear. Now, think about the optimization problem, an analytical form of a function, and another analytical form of a function. But there is this constraint that we don't know how to write it. But for that, we have data set. So maybe if we have this data set, for the constraint that we don't know how to write explicitly in an analytical form, maybe we can use a machine learning model. If we do that, we have a constraint which is learned by one of these difficult machine learning models. And then what happens is we can really solve the overall problem. Now, this is very general, and this can really happen in real life. And one example that we had also in our paper was word food programs, the palatability constraint. So palatability meaning that you're going to really come up with this food baskets, and you want this food basket to be something that people would taste and enjoy. We have the data set where for different ingredients, people said that this is, let's say, delicious, not delicious, and so on. I don't know what this relationship is because I don't have the function, but I can really fit any one of these models, then put it in, maybe do some sort of a distribution problem because this is an overall optimization problem that we can solve. So this was the core idea of constraint learning. And we have also a Python package for that. You can always download and play around. Okay. Nice. So where do we use it in interpretability? For that, let me talk about counterfactual explanations. Everything, I think, more or less started in 2018. There was this important paper in Harvard Journal of Law and Technology. And these gentlemen and this lady, they were talking about counterfactual explanations, saying that maybe if there is a black box model, we don't need to really understand what the black box model itself does. But maybe for one sample, which is in our example about this loan, you going there and being rejected, maybe we can find a close enough another sample, and that sample will be used as an explanation. Apparently in psychology, this is also something accepted as a nice explanation, because I also find it explaining. I go to a bank, they don't give me a loan, and they're just going to tell me that because that's a counterfactual that they're going to present. Look, this is a fictitious person, and this fictitious person is almost your age, has almost your salary, but let's say she has a car. So, but she gets a loan, I don't get a loan, then I will think, okay, maybe I should also get a car or something like that. Okay. And as you can see, I wanted to put these here because these are some nice papers to take a look at. And these are all very recent. So that also shows how hot this topic is. Now, an example that I took from Verma et al. This paper, and this also shows these are the people, let's say, who are accepted and were rejected, or 1, 0, plus, minus, whatever you want to call it. This is a decision boundary. And here is me. I am rejected. They didn't give me a loan. And very close to counterfactuals that they can produce using the discussions here. And these are basically those people who would be given loan, and they're really close to me. So I find it a good explanation. Now, after seeing this, we said, okay, this is an excellent example for optical, because here is one X bar counterfactual that we're trying to find, and the prediction will be Y bar, right? And what do I want? I want a counterfactual, which is X, and it will minimize the distance, meaning that really close to, so this could be me, I'm rejected, this is 0 now. And I'm searching for another fictitious person really close to me, minimize the distance, but she will be accepted. This is Y, in this case 1. So if you look at this, this is nothing but what we were trying to do in optical. And you can use any one of these methods. We did, and we also use some tricks from optimization to make sure that the solutions that we are obtaining make sense. You don't really get a solution which is really farther down here. So it will be somehow represented with the data set. So this is a technical detail, but we were able to come up with these plots. So this is me being rejected, and these are two particular people, and they would have been accepted, or vice versa. And you can also do these areas that you check. You can really look at the entire data set that's really done with these constraints, or you can also only look at those who are being accepted. Okay, and then the solution will change. The solutions were here and there, and now these are the two solutions that they will be provided to me as an example, saying that these are two fictitious examples. As you can see, they're not in the data set, and they will have been accepted. So in the last couple of minutes, I want to maybe raise a discussion. Interpretable machine learning, and as I said, I'm interested in that. It's an interesting subject. It also allows constraint optimization, which I am quite fond of. But there are also things that we need to, I guess, discuss, and many people are looking into that. The question is, what is interpretable? Which sounds like a strange question, but it's really the question. I mean, all people like me, more geeks and nerds, we are trying to come up with these algorithms, but maybe in different fields. The things that we are developing, they don't really find it easy to understand or explainable or interpretable. So the question of interpretability need to be also examined thoroughly. Okay, people maybe should do surveys, which we are also planning to do one in healthcare in different domains, looking at what they would consider as interpretable. Why am I asking this question? Here is unboxing. I said that there will be this data, different features, and there's this data set, and we were just trying to come up with these description explanations. It could be decision trees. We also said that we can give some local explanations like less, right? Remember, we were coming up with these local explanations when everything is linear, and or linear regression. We also talked about the counterfactuals. Now, apparently, I claim, so I'm criticizing somehow also myself, these are interpretable because these are the ones that I used. Linear regression, counterfactual plot, or the examples that we developed, and also decision trees and decision rules. Now, apparently, I claim that linear regression is interpretable. Remember, this was the relationship. You have P features, and for P features, you're going to have different weights. This is, if you ask me, very clear. But how about this one? This is also linear regression. I have 51 different features, and they all get some small weights. Now, I'm not sure whether in different domains they will find it interpretable, although we have very powerful statistics with this. How about decision trees? Because this is something that I am also using and calling it interpretable. And whenever we talk about decision trees, it's just the one that you see on the left. Beautiful, right? It's easy to understand. Everybody would be happy with it. But how about this one? This may be more accurate than this one, but that's really difficult to understand. Maybe all decision trees are not interpretable, or maybe in certain domains, let's say in regression, and that's to my experience, the decision trees become very large. Are they really interpretable? I don't know. How about rule-based methods? This is a rule that we have used in our paper. Okay, very simple to understand. Only 3 rules, some simple if-then rules. But how about this one? This is from a paper. Many rules, and they're all mixed together. It's maybe very difficult to interpret. Counterfactual explanations. I said, and people also said it since 2018-19, many papers written. So this is, okay, maybe this is a nice counterfactual explanation. But how about this one? If I really obtain a solution when the factual instance is here and I obtain a counterfactual, it's really farther away. Maybe this is not a good explanation. This is not really close. This is me, 48 years old and with a certain salary, and this is a young guru making 5 times more than I do, and then he's accepted. So these are really difficult questions. We are always saying that these are nice interpretations, nice interpretable models, counterfactuals, rules, decision trees, linear regression, but I think they should be all taken with a grain of salt, because these things are really problem dependent and domain dependent. Okay, with this, I am ready to wrap up. We are now working on a survey in healthcare and trying to ask people who are using these algorithms, clinicians, and asking them to tell us what is actually interpretable. We are trying to collaborate with people and get some feedback, and these collaborations are going on, and I have already shown you a couple of those, and we are going to have more. We need applications because these things by themselves, they're not that useful unless you prove that they really work in these different applications. So we are very open to working with other people in applications. And of course, testing, improving, because these things, when people use, they will just come back and say that you did something stupid, and we fixed it, and we improve it, test it again, and so on. With this, I thank the organizers again and finish my talk. Thank you.
Thank you very much, Professor Birbil. It was a great talk. So for the questions, I would like to start with one. Remember, this is a organization targeting for the undergrad students. So I would like to ask some general question. For example, what happens if a model is not interpretable? What are the consequences? Especially your domain is business, but maybe you are working in another application domains. So maybe you can give an idea about what can go wrong with this machine learning models.
Of course. How about let's talk about the one not in business where people are actually using, but somehow researchers are using it. So some of these undergraduate friends here, they will maybe become researchers themselves, correct? And there is an algorithm, and we don't really know what it does. Let's say a deep learning model, okay? Everybody really wants to understand so that we can really build better models. This is the way it goes. I mean, it works well because of this reason and that reason. If somebody tells, maybe there will be some other models that we can do. So it's not just about trying to help decision makers to understand what's going on about their decisions, but it also helps the research. So I gave all these examples throughout my talk, giving a loan. Yeah, okay, that's required for banks, that's business. But that could be also in healthcare, right? Some people will be diagnosed with some diseases, and these diseases are now more accurately diagnosed by some machine learning algorithm. But then if you want to develop, I don't know, some drugs for that particular disease, maybe it will be really nice if we understand what the algorithm does exactly. So it goes hand in hand. I think the implications are abundant, and there are, as I said, cases that we should also look, for instance, like fairness example that I gave, because bias is a huge problem. When you use machine learning, you are using past data, and we know that the past data is not free of bias. I mean, in the past, we are using all this data. We all know that the females were rewarded less salaries than male, right? That's in the data. And when we use that data and do a prediction, and we are just checking whether it's accurate, it may be super accurate, which means that we are just repeating what has been done in the past. So the bias, the unfairness is in there. Although the algorithm seems to be very powerful, it just repeats it. So if we understand what the algorithm does, like the example I gave, then we can go back and say that, okay, this data is tainted, we should not use it. We should do something about the bias in the data. That type of thing.
Okay, thank you. And I also would like to ask, for example, in your talk, you mentioned the software tools for your algorithms implemented, and probably the students will go there and download it and will try those algorithms, okay?
Excellent.
But what kind of application do you suggest, or what kind of data sets do you suggest for them to try those algorithms?
Sure. For instance, let's talk about LESS, because rule discovery will be updated soon, but LESS is now at least version 0.2. It's more usable. I would certainly suggest playing around with some data sets that they can find on internet. And to make a project out of it, they can also maybe enter the Kaggle competitions. Kaggle is a website that is Kaggle for those who don't know. That's why I wanted to spell it out. Over there, they have all these different competitions, some of them with some prizes. But if you really go onto those competitions and use, let's say, less, and if you can really beat the others, I think that's also good reputation. But I think it's not just about the competition. Playing around with data sets is the best way to understand more. I mean, I teach machine learning, but I always tell my students that, yeah, technical part, I can explain, it's not difficult. But when you start doing it yourself, then you understand more.
Yeah, I certainly agree that students should go there, download those codes, and start to play with, and they can see the problems itself, which is very important. Then for the advanced degrees, they can actually try to solve that problem. So I also suggest this hands-on approach for this machine.
I agree. Yeah, I'm a more technical guy with mathematical optimization and so on. But if I have an idea, I also try it myself. I play around, maybe sometimes I write a small script. So it's always a good idea.
Okay. And what about, for example, let's go more basics. So there is a student and try to, he or she is curious about machine learning, but he doesn't know the programming and anything about that, doesn't know mathematics, for example. So what kind of the fundamentals for the maths or the programming coding, what do you suggest?
I mean, I always make this joke, but throughout my life, I only use calculus and linear algebra. Probably for electrical engineers, they also use differential equations, but I never used it. So for machine learning, I would say a proper background in linear algebra, and I'm really talking about undergraduate level, and calculus 1, 2, is a really good start. And as you advance, then you can maybe start looking into numerical linear algebra and so on. But to start with, I think just elementary linear algebra is good. And I regret that I didn't pay that much attention to statistics, but I wish I had. And that will be my other suggestion. I mean, learn statistics. Statistics is a beautiful field, yes, and very well developed field. And when it comes to coding, I mean, I have switched to Python. I started with, I don't know, Pascal, moved on to C, Java, MATLAB, many things. But now I feel like that Python is very simple and a good way to go for this type of work, unless you're in robotics where you would need speed and stuff. That's a different story. But for machine learning, to try things out, to learn the basics, Python is a good tool. And we have, if you want to start with Python, we have a blog called veridefteri.com, and there Kaan Öztürk has written very nice set of notes in Turkish to start with Python. I think it's beautifully written. That will be my suggestion.
Yeah, I also agree that the programming language is not that important, but Python is very developed, so probably it is a good choice to start with.
Yeah, it's like Legos. You just put the things together and it works. And like linear algebra, I said you learn linear algebra, move on to numerical linear algebra later on. You can start with Python to get some feeling of coding, but if you want to excel, you need to learn object-oriented programming, data structures. Of course, I'm not underestimating those important subjects. What I'm saying is it's good to really dive in immediately and try to get your hands dirty.
Okay, so the final question, I think, I wonder, this is also my personal question, is that I try to follow the news about this machine learning, the artificial intelligence, and all the discussion about this deep learning versus the symbol discovery, for example. I think that your work is very related into these discussions, and you know, there is a camp for the deep learning, there's a camp for the symbol discovery, if you follow the recent discussion. So I would like to wonder your opinion, those symbols especially, and how should they enter into this picture of machine learning? I think the interpretability is one of the way, but you can see another ways.
So is the question about following up the news, or is it really about where to start?
About my question is about the symbols, actually. So what is the role in general picture of machine learning? These rules, for example.
I see. I mean, it's hard to say. And I think one important reason for that is computer vision. And let me try to elaborate on that. I know that there are also interpretation methods in computer vision, of course. Image processing is a hugely developed field and a very important field, right? If you think about all these scans of in healthcare, that's also being used and so on. And there, the success of deep learning is immense. So people not really let it go. And I think they shouldn't, of course. But I also feel like that for some problems, it's an overkill. And I had an example about that recently for a data set where a friend of mine was just using simple decision tree and getting a result almost as good as XGBoost. XGBoost is a very powerful ensemble method. So there is this, I have the same tendency as well. There is this thing that people immediately try things out, right? Because it's now very cheap and very simple. But really going back to the data, working on the data, getting some statistics and feeling of it is, I believe, way more important than the method that they are using. So I think the difficulty or the, let's say, expertise for this younger generation will be what should be used, and are we going to really pick the proper tool? So the accuracy of decision tree is 0.98, okay, 98%. That you have all these deep learning models, it's 99%. Is it really worth it? I don't know. I don't think so. And there had been also some interesting papers recently where people use very engineered, very sophisticated neural networks, and people with some simple heuristics, they obtained close enough solutions. Of course, they're not really mocking each other. This is science, right? We all try to do certain things. But at one point, I feel in the next 3 years or so, there will be this refinement in the sense that we are not going to really shoot everything with a bazooka. There are these other tools that we can use. That will come. And for those who want to really start, I would say try them out. It's really, really very easy. There's so much things on the web. I sometimes feel that these instructors we are becoming obsolete.
Okay, so I think those are very valuable advice for our students. So I learned a lot of things from your talk, and I also think the same for our students. They will watch this in later and in the YouTube page of the IEEE Turkey section. So
excellent.
I think this would be a good resource for the future generation of the AI and the machine learning engineers, and they will learn this interpretability built into their models, I guess. So we have.
I hope so.
Yeah.
I hope so. Okay, they can always write to me, because we are the ones who are writing these codes and the papers. Yes. There could be always some errors, bugs. If they see something, or if they have some suggestions, just please write to me. That will be nice.
Yes. So thank you very much for your time, for your talk. And I think we can stop here, and we can say that our students go and try those models and see the problems associated with all this machine learning and make it better in the future, right?
Okay. Yeah. Thanks a lot to all of you for organizing this, starting with Murat, Serhan, Doğan, and Seda Nur. That was a pleasure to be here.
Thank you very much, Professor Birbil. One more time. Now, we are closing this session, and we will start a new live stream on IEEE YouTube channel for the presentations. Thank you.